This is the final problem in the test bank, and I want you to review this one specifically because um, we know that the force is the derivative of negative derivative of the potential energy. And this is going to be very closely related to a formula that we are going to use in E&M, namely that the electric field is the negative derivative of the voltage um, or the potential difference. So we're actually going to be relating these two things later on. That's just a preview of where we're going because electric field is to force as voltage is to potential energy. So this is what we're working with, and let's just jump into the problem now. So we want the total mechanical energy of the object. Let's remember, mechanical energy means kinetic, means EK plus potential. And since there's no friction, energy is conserved here. And so that means we can say 1/2 mv squared plus u of x. And let's see if they give us any kind of speed and position that we can work at. So it turns out that we're at negative 0.5. The speed is 2 meters per second. So we can say 1/2 times 3 times 2 squared plus 4.0 times negative 0.5 squared. So that's the energy at negative 0.5 meters when we're going 2 meters per second. But since energy is conserved, that total number is never going to change. So we can then just say that our total energy ends up being 7 joules when we add this up. Now it says calculate the x-coordinate of any points at which the object has 0 kinetic energy. So let's be clear on how that works. Since the total energy is 7 joules, we can say 7 equals 1/2 mv squared plus 4.0 x squared. And the thing is, we have 0 kinetic energy when the speed's 0. So we can then say, let's find out the points where all of the energy is stored as potential energy. So that means x is the square root of 7/4 actually gives us the plus or minus square root of 7/4 is where we get the points where there is no kinetic energy. Then for part C, it says, calculate the magnitude of the momentum of the object at 0.6 meters. So let's get V at 6 meters in the following manner. And then we'll take P equals M times V, where V is what the speed is when we're at 6 meters. So here we go. We know 7 equals 1/2 3V squared plus 4.0 times 0.6 squared. So we can actually isolate V here. So 7 is 1.5 V squared plus, and then we'll take 0.36 times 4, which is going to give us 1.44. And so we're going to end up solving for V. And when we do that, we'll end up getting that V is 1.93 meters per second. Finally, in part D, it says calculate the magnitude of the acceleration of the object as it passes x equals 0.6 meters. This is actually a little bit of a trick. Since f is negative du dx, what we'll do is we'll take the derivative and we'll set it equal to ma. So negative du dx equals ma, because ma equals f. And then what we'll do is we'll take 1 over m and multiply it by negative du dx, at the point in question, and that will give us the acceleration. So we're going to take 1 over 3, and then we're going to take the derivative, so that's going to give us 8.0 times x. So that'll be negative 8.0 times x equals a. And we're doing that at the point 0.6. So when we multiply all this out, 8 times 0.6 is 4.8 divided by 3 is, we're going to get negative 1.6 meters per second squared equals a. And I believe that is the last problem in the test bank, so I will get these uploaded to PowerSchool now.